Welcome back to Analog Electronics. This is lecture 24. Today we are going to talk about circuits which are using op amps. So, in the last class we had started discussing op amp based circuits, adders, subtractors, right. So, the idea was always to use superposition whenever there are more than one input. So, the adder circuit was right. So, you add two currents and then push it through a feedback resistor. So, this was basically the idea. So, I 1 is V 1 by R 1 and that has nowhere to go but through R 3, and likewise I 2 is V 2 by R 2 and that has nowhere to go but through R 3, there is no alternative. Okay. And the current going through R 3 is the sum of V 1 by R 1 plus V 2 by R 2, and therefore, the drop across R 3 is R 3 times V 1 by R 1 plus V 2 by R 2. This is the drop across R 3 and it starts from a potential of 0. So, it ends at a negative potential of minus R 3 times V 1 by R 1 plus V 2 by R 2. So, this is basically the idea in this case. All right. So, this was the adder. So, the reason why we called this an adder is because the currents got added. Okay. Otherwise, this is pretty much the operation, you get an addition and also an inversion. The other one, which is the subtractor, is using the two different terminals of the op amp. Okay. So, in this case you apply superposition again. So, the voltage at the plus terminal is V 2 times R 2 by R 1 plus R 2, because it is a potential divider. This voltage is going to be amplified by a factor 1 plus R 4 by R 3. Okay. So, you have got, if I apply only V 2 and V 1 is ground, then to start with the voltage at the positive terminal is V 2 into R 2 by R 1 plus R 2. This voltage is going to be amplified by a factor, remember V 1 is ground, this node is at ground, this node is V 2 times R 2 by R 1 plus R 2. So, you get the non-inverting amplifier configuration, and therefore, the voltage at the output V out is the voltage at the plus terminal times 1 plus R 4 by R 3. Okay. So, this is the gain from V 2 to the output, and likewise there is a gain going from V 1 to the output. When you do V 1 to the output, V 2 is going to be at ground, but then potential division will ensure that the voltage at the plus terminal is also 0 volts, right. So, with V 1 it is just minus R 4 by R 3. So, this is the overall idea. Now, if you want these factors to be equal, then you can engineer them to be equal. All you have to do is, what do you have to do? If you want to make sure that they are equal, you just make R4 plus R3 equal to R1 plus R2. So, these two cancel out and this therefore becomes, so make R4 equal to R2, make R1 equal to R3, alright. If I make R4 equal to R2 and R1 equal to R3, then what is going to happen? R4 plus R3 is the same as R1 plus R2. So, these two will cancel out. R3 is the same as R1. So, this is V2 times R2 by R1. R4 by R3 is R2 by R1. So, overall you get R2 by R1 times V2 minus V1. Okay. Anyway, this is just playing with values. You can figure out, you can instead of doing just an addition or just a subtraction, you can do a weighted addition, weighted subtraction by utilizing the values of R1, R2, R3, R4. Okay. So, this is just addition and subtraction operations. The op amp can also be used to do other more interesting operations, for example, integration and differentiation. So, if this were to be a resistor and the minus terminal is at ground, then this current is going to, if it was R, then the current would be input divided by R, right. But now that this I have placed a capacitor over there, if I have an input voltage V in of t, then what is the current? If this is C, C dV by dt, right. So, C dV in of t by dt. So, this current goes in, it has nowhere to go but to go through R, and therefore, it creates a potential drop across R, right, and therefore, the output voltage V out of t is equal to minus R C times d V in dt. Okay. So, this is called a differentiating circuit, a differentiator, and likewise you can make an integrator. What is going to happen here? If this node is at 0, then the current coming in is nothing but V in by R, okay, and this current is forced to go through the capacitor, it has no other way to go, and therefore, if I know the current going into a capacitor, the voltage developed across the capacitor is proportional to the integral of the current, right. C dV by dt is the current. So, the voltage is integral of, so I is C dV by dt for a capacitor. So, voltage is integral I by C, correct, for a capacitor. So, in this case I know the current is V in by R, therefore, the voltage drop across the capacitor is 1 by C times integral V in of t by R dt. That is the voltage drop across the capacitor, or in other words V out. So, this is the voltage drop. So, V out is at the minus terminal. So, V out of t is equal to minus 1 by R C integral V in t dt. So, this is the way it works. Now, there is a problem with the integral. This integral is definite or indefinite. Basically, you start at time t equal to minus infinity and you keep integrating, right. And since we do not know the history of the circuit, it is not very clear how to do the job, all right. So, you can do it this way, you can keep an indefinite integral and then you can add a constant to it, right, an arbitrary constant which indicates the starting point. Now, invariably what happens is that this arbitrary constant is going to be such that the circuit is no longer going to work. Okay. So, this circuit does not really work like this. The integrator does not work. The reason why it does not work is because there is an arbitrary constant, and this arbitrary constant can be anything. It can even be equal to VDD, or it can even be equal to the minus supply or whatever you want, right. And as a result, the circuit is going to clamp to the power supply and the op amp is not going to work. There is one more way of seeing this. If you look at this particular circuit, then at DC, when you try to work out the DC operating point, at DC this capacitor is an open circuit, okay, it does not exist at DC, which means that there is no feedback around the op amp. And therefore, you remember in the last class we had those curves, we had the KCL curve and then we had the op amp curve and then we had the point of intersection. All of that does not really apply anymore, because this KCL does not really work out for you, this capacitor is not there. Okay. So, all these currents are 0. So, that KCL curve is no longer there. So, you can be anywhere on the op amp curve. Whenever you can be anywhere on the op amp curve, right, Murphy, you know Murphy's laws. So, Murphy says that if something can go wrong, it is certainly going to go wrong. Okay. So, this is one of those situations where Murphy is going to take over charge, right. Murphy is going to declare that this op amp is not supposed to work, it is not going to work at all. So, the reason why it did not work is the absence of negative feedback at DC. So, if someone asks you what is the reason, why did this op amp not work, right, why does this circuit not work, in that case you will have to give the answer that this circuit does not have negative feedback at DC. If you give this answer, it is a complete answer. Okay. Otherwise, you will have to draw all kinds of curves, you will have to show that there is no KCL going on over here, you draw the op amp curve, it is still beating around the bush, right. You can say that there is a constant of integration, you are still beating around the bush. Okay. The correct precise answer, why does this circuit not work? This circuit does not work because there is no negative feedback at DC, and therefore, the DC operating point of the op amp is not established. Okay. You want a nice clean operating point such that the op amp has high gain, okay, and that does not get established when you have this kind of a circuit. So, this integrator is nice in theory, but it does not work. However, we are smart, we make it work, right. We make it work in a scenario where this integrator is part of a subsystem and overall there is DC negative feedback to establish the operating point from outside. Okay. So, a higher circuit. So, at this level of abstraction this circuit does not work, but if I use this circuit as part of a bigger block, let us say in a circuit that looks like this. So, this is one integrator, there is another integrator. Okay, let us say this is not just an integrator, let us give some damping to it. Something like this. Okay, so you have got an integrator which is part of a bigger system, or you could even have this. Okay, you can construct many different scenarios. So, this is an integrator by itself. This circuit by itself is an integrator. Standalone it is not going to work, but when it is part of this bigger circuit it is going to work. Why is it going to work? Because hopefully there is negative feedback at DC, and that is going to establish the DC operating point. So, let us see. Okay. Let us do an example. Let us take this particular circuit as an example. All right. So, let us take this as an example. Let us say all the resistors have value R, and let us say the capacitor, the first one is C1, the next one is C2, all resistors have value R. All right. This is the circuit. Now, what happens over here? How do I see, how do I check that this particular op amp has negative feedback at DC? I need to check that. So, suppose the voltage at this node is slightly high, slightly higher than the requisite voltage to give it high gain, right. The op amp should be in this region. Remember, in the previous discussion we discussed the op amp has to be in this high gain region, right. The other two regions are flat, there is no gain, the op amp has to be in the high gain region. So, the operating point of the op amp, that input voltage of the op amp has to be such that you are in this region. Okay. So, let us say you are not, you are slightly higher, you are slightly higher over here, you are somewhere over here. In which case, what does this mean? What is the output of the op amp? It is the lower power supply, right. You are slightly higher than required. So, therefore, this is very low. Fine. You have got an R, another R. So, therefore, what is the output over here? Just the opposite, right. It is a gain of -1. So, the voltage here is equal and opposite. Fine. Now, that is getting fed back to the first op amp. So, the input to the first op amp, one of the two inputs to the first op amp has a very high voltage, right, which means lots of current is going to come in. If lots of current comes in, then what is going to happen? All that current is going to go through this resistor. Remember, C1 is open circuit at DC, so it does not matter, we are talking about DC only, C1 is not there at DC. So, all of that extra current, because this is high voltage, is going to come through this resistor R, a lot of current, all of that current is going to flow through this R right over here. Why this R? Why not the other R? Because the other R is right now, this side is also at ground. We are thinking superposition. Okay. So, you think superposition, this side is at ground, this node is at ground. So, this can't carry any current. Okay. So, all of that current is going through this R, which means that the voltage here is going to be exactly the same, negative. Okay. So, a slight increase in voltage caused a drop in voltage over here, and this there is no current in this branch. So, the voltage over here is the same as, it is going to pull this particular node back down. Okay. So, that is negative feedback for you. You create a slight disturbance, a slight positive disturbance, a force comes back and pulls you down. Okay. If you had a slight negative disturbance at the same spot, then the force would come back and push it up. Alright. So, that is DC negative feedback. With the help of DC negative feedback, the operating point of this op amp is established, and therefore, the integrator is going to work under these circumstances inside this bigger circuit. Okay. It is not going to work standalone, it is going to work as part of a bigger circuit. Now, just as an interesting exercise, can we analyze this particular circuit? It is a very interesting circuit, it is actually a very famous circuit. I am going to tell you the name of the circuit after we analyze it. Okay. So, let us first analyze the circuit. I am going to draw it for your benefit yet again. Okay. Of course, you can have different values of R, they do not necessarily have to be all equal, but without any loss of generality, just so that my analysis is easy, right. I want to reach some answer quickly. So, therefore, I have placed everything as equal. However, in a certain situation you might want these resistor values to be different. There is no reason for them to be equal, no other reason for them to be equal. Only reason why they are equal is so that my analysis is easy right now in front of you. Okay. A very bad reason, but that is what it is. Right. Now, we have already established that all the op amps have DC negative feedback. By the way, this op amp also, the first op amp has DC negative feedback because you have got an R. Okay. The third op amp also has, obviously has DC negative feedback, you do not have to worry about it. Okay. Now, let us see, let us call this voltage V1, V2, and if this is V2, what is the output? The output is obviously minus V2, because this is R and R, this is an inverting amplifier. Okay. There is a relationship between V1 and V2. V1 by R is the current coming in over here, that current goes through C2, and therefore, V2 is equal to minus 1 by SC2R V1. Okay, that is the integrator relationship. Fine. Now, the current here is V in by R, the current this way is minus V 2 by R, all right, and the current through the capacitor C 1 is V 1 times S C 1. The current through this R is V 1 by R, and if you do a KCL at this node, okay, what do you get? You get V in by R plus V 1 by R minus V 2 by R plus V 1 times S C 1 is equal to 0. Fine. I did it this way because there were many branches over there. Okay, it was not really straightforward. What else could be done? Fine. So, my assumption is that this node is at 0 volts, which is more or less correct because the op amp is in its high gain region because of DC negative feedback. And then with that assumption in mind, this current is minus V 2 by R, this is V in by R, this current is V 1 by R, this current is V 1 times S C 1, and the sum of all of these currents is equal to 0, KCL. Okay. And over here we already know V 2 relationship between V 2 and V 1. So, let us say that V 2 is my desired output quantity. If I think that V 2 is my output of the circuit or minus V 2 is the output of the circuit, then we are going to replace all the V 1s in the equation with V 2. So, let us replace. So, V 1 is minus S C 2 R times V 2, right, and let us replace all the V 1s with V 2s. So, I have V in by R minus S C 2 R cancels out V 2 minus V 2 by R minus S squared C 1 C 2 R V 2. Okay. And something very convenient over here would be to multiply the entire equation by a factor R. Okay. So, if I multiply the whole thing by R, this is what I get. First term becomes V in, the second term becomes S C 2 R times V 2. Why did I do that? So that all the terms have dimensions of voltage. So, the first term is voltage, the second term is S, which is 1 by time, times C 2 R, which is time. So, 1 by time times time is nothing, times V 2. So, the second term is voltage, third term is V 2, so it is voltage, fourth term is S squared, which is times 1 by time squared, times C 1 R, which is time, C 2 R, which is time. Okay. So, the second term is also just voltage. So, all the terms are now in terms of voltages. Okay. And next what do? You compile all the V 2s together. So, V in is equal to V 2 into S squared C 1 C 2 R squared plus S C 2 R plus 1, all right, or in other words, you have created V 2 by V in is equal to 1 by 1 plus S C 2 R plus S squared C 1 C 2 R squared. Okay. And this pretty much means that you can create an arbitrary second order low pass transfer function, right. You have got full control over the value of C 2 R, right, just have to choose the right time constant. And then if I know C 2 R, you have full control over the value of the second term also, you can choose any value that you want. So, you know all you have to do is choose the right C 1 times R. Okay. Remember, the denominator looks somewhat like this, right, 1 plus S 2 times S, what was it, zeta, omega n. Something like this. Okay. It does not really matter. Okay. So, you have got two control objectives, one is zeta, the other is omega n, and you can fix them with the help of the two time constants C 2 R and C 1 R. All right. And in any case, as I said before, R, I have chosen all the values to be equal to R. It need not be the case, you can mix and match, right. Okay. So, this gives you an arbitrary low pass transfer function. Now, remember V 1 is nothing but S C 2 R minus S C 2 R times V 2. So, if you pick V 2, if you pick V 1 as your output, then you pretty much get something else in the numerator, right. The denominator remains the same, you get something in the numerator. So, this is, if you look at it carefully, this is a band pass transfer function. Okay. And with the help of V in, V 1 and V 2, you can arbitrarily add V in, V 1 and V 2 and wait and add, you can create any second order numerator polynomial as well as any arbitrary second order denominator polynomial. All you have to do is weight the coefficients, right. You already know how to make adders and subtractors, right, and then add and subtract appropriately. So, one more op amp, add and subtract appropriately, and you can create any arbitrary second order numerator by any arbitrary second order denominator. All right. So, this particular circuit is called a biquad, in short for a biquadratic circuit. It is named after the first person who made it, it is called the Tau-Thomas biquad. Okay. And it is a fantastic circuit because you can create any arbitrary second order transfer function with the help of this circuit, with the possible addition of one extra op amp. So, 3 op amps plus one more and that is it. You can create any arbitrary second order transfer function, numerator by denominator. All right. This is something that is used by a lot of people to make filters, to design filters, low pass filters, high pass filters, band pass filters, right. Band stop, you can make anything, as I said. All filters can be designed with the help of this. So, a lot of people fall back on this. A lot of people, what they do is, when they see that they need to make a complicated filter transfer function, some numerator divided by some denominator. Then they break up the denominator into pieces which are second order and first order, right. It is always possible to factorize, you figure out where are the poles of the denominator. So, the denominator will have some complex conjugate poles and some real poles, right. So, you take the complex conjugate poles, those are second order sections. Okay. You take the real poles, those can be treated as first order sections, or you can combine them, two of them, to get one more second order section, right. And then you arrange the denominator as many second order sections and maybe a first order section, right. And then you make that many number of biquad circuits, each biquad circuit trying to representing one of those second order sections, right. The first order section does not really need much discussion, it is just one of these. The first, just the first one will give you a first order section. So, you do not really have to work very hard for a first order section, okay. But the second order sections might need work, and this is how you make the second order sections. You just cascade all of these second order sections and make any arbitrary filter transfer function or any arbitrary transfer function. You have h of s, some numerator, some denominator, factorize numerator, factorize denominator, collect all the poles, right, smartly. You have to smartly collect the poles. If you are unsmart about it, bad things will happen, right. So, you smartly collect all the poles, you smartly collect all the zeros, right, pair of poles by pair of zeros, one tau Thomas biquad, another pair of poles by pair of zeros, another tau Thomas biquad, right, and then 2 or 3 sections, 3 sections will give you a 6th order numerator by a 6th order denominator. Invariably for low pass filters, the numerator is not even required, numerator is 1. For a lot of low pass filters, for a lot of, not all, lot of low pass filters, numerator is just 1, in which case nothing much is required with the numerator. Okay. Some if you try to be smart with the low pass filter, then the numerator will not be 1 anymore, right. There might be zeros in the numerator polynomial. Okay. If you try to place zeros in the numerator, then you will have to work with the numerator polynomial as well, but you understand how to work with the numerator polynomial. All you have to do is add weight and add V in, V1 and V2, okay. And that will get you the zeros. Otherwise, standard low pass ones, especially if you try to make Butterworth and Chebyshev responses, or even Bessel filters, Butterworth filters, Chebyshev filters, those are all pole, there are no zeros in those. So, you do not bother about the zeros, you just make it with a tau Thomas biquad, multiple sections. So, you might have studied other strategies in circuit theory. In circuit theory, you would have studied strategies where you build the circuit with the help of a ladder with inductors, capacitors, sometimes even mutual inductances, right. You can do it with op amps, right, and with op amps it is not a very big struggle. All you need to know is what is the numerator, what is the denominator, factorize using MATLAB or any other program, you know the exact locations of the poles, exact locations of the zeros, and then you smartly collect them, and that is it, right. It all falls in place, there is no, you do not have to iterate too much. All right. Now, of course, this is all fine, but the technique that you learnt in circuit theory is actually the better one. Okay. This is fine, this will work out to some extent, but whenever you try to make complicated polynomials, right, higher order systems, anything more than third order, if you try to implement anything more than third order, things are not really going to work out very smoothly if you try to do it with the tau Thomas biquad. But otherwise the tau Thomas biquad is a very nice approach, because cleanly you get the whole system in one shot. Okay. Let us discuss some more op amp circuits. So, this is a fantastic op amp circuit which is used all the time. A lot of people like making filters with the help of the Tau Thomas biquad, because it is so easy to make. Okay. Just by the way, this is out of context, but filter design is actually a nice subject, and not a lot of people know how to design filters. So, those who do not really know how to design filters, right, invariably for them a shortcut is the Tau Thomas biquad, break up into second order, first order polynomials, it is easy to understand, and then implement using Tau Thomas. Now, those who know filter design, they will tell you that do not do it that way, do a full ladder network, because that will give you far better performance. Okay? And then the ladder network can also be transformed into a circuit that uses op amps. We will not do that right now. What I would rather do is another second order circuit, that is an extension of this one. So, by the way, this Tau Thomas biquad, I have drawn it 3 times today already, but is there, I mean, am I drawing it out of memory? Have I memorized it, the circuit, or am I constructing it? So, it turns out that it is very easy, very straightforward to memorize the circuit. You do not have to be, it does not take much. The first stage is a damped integrator. The second stage is a pure integrator. So, the second stage is an integrator. The first stage is a damped integrator, an extra R. So, damped integrator, integrator. The third stage is nothing much, it is -1 feedback. Okay? It is very easy to memorize, damped integrator, integrator, -1 feedback. So, the circuit I am going to draw now is going to be an integrator, another integrator, -1. So, instead of damped I made it a pure integrator, and then I am going to apply feedback, and in this case I am not going to bother with the input is the feedback. So, without any loss of generality, I am going to assume all the resistors are equal, and let us also assume all the capacitors are equal without any loss of generality. In the earlier case, if I assumed that the capacitors were equal, I would lose generality, because I would not have been able to synthesize the two denominator coefficients. Okay, you had one and then you had one more coefficient and one more, right. So, those two coefficients I would not have been able to synthesize, because I would not have enough degrees of freedom, right. In this circuit, let us just make it all equal, all R's are equal, all C's are equal, okay. Forget about the degrees of freedom. So, only 1 degree of freedom, fine. Now, you are going to say what kind of circuit is this? It does not have an input, and yeah, I agree, it is a very funny, a very strange circuit which does not have an input. Let us just think about it for a little bit. Let us assume this voltage is V2 like before. So, the voltage out here is going to be minus V 2 because this is just minus 1. So, minus V 2 over here, and therefore, the voltage at the output of the first integrator is going to be minus 1 by SCR times minus V 2. So, this is going to be minus 1 by SCR, which is the integrator, times V 2. So, it is going to be plus V 2 by SCR. Okay. And then V 2 by SCR is being integrated and you are getting V 2 back. So, if you integrate V 2 by SCR, what do you get? V 2 by SCR into minus 1 by SCR. Okay. And that happens to be equal to V 2. This is very strange, right? It is not really looking nice. It is not looking nice at all. All right, let us look at it in the time domain. When things do not work out in the frequency domain, lot of times it might be nicer to move to the time domain where things are a little more tractable. Okay, let us think. This is V 2 of minus V 2 of t. This is minus V 2 of t. This is V 2 of t. Okay. And this was V 1 of t, which is fine. I will just write out what is happening. So, I have got minus V 2 of t that goes through R, right, and that is pushed through the capacitor. So, the voltage, this is V 1 of t. V 1 of t is nothing but minus V 2 of t by R C integral dt. Okay, minus of that. All right. Now, lot of times you do not feel nice with these definite integrals, right. So, you can write it in a slightly different way. You could write it as the differential of V 1, right. So, if I do R C times d V 1 t dt, then that will be V 2. Fine. So, all I am saying is that instead of saying V 1 is the integral of V 2, let us say minus V 2 is the differential of V 1. Okay. So, minus V 2 is the differential of V 1. Let us look at it backwards. And likewise, V 1 is the differential of V 2. Okay. So, V 1 of t is nothing but minus R C d V 2 dt. And then V 2 is R C d V 1 dt, which what does it mean? It means V 2 is nothing but minus R squared C squared d squared V 2 by dt squared, or in other words, you have magically arrived at the harmonic oscillator equation, right. This is the oscillator equation, right. V 2 is some minus something times V 2 double dot. Okay. And what does this mean? This means that this circuit is going to oscillate at what frequency? At frequency of 1 by RC. So, omega naught is going to be 1 by RC, omega, the angular frequency is going to be 1 by RC, fine. So, in other words, V 2 of t is going to be something, some amplitude, unknown amplitude times cos omega naught t plus some unknown phase, where omega naught is nothing but 1 by RC. Any questions so far? So, this particular circuit, it's an oscillator. It's one of the few oscillator circuits that actually gives you a pure sine wave. Okay, the reason why it gives you a sine wave is because it oscillates at this frequency and only at this frequency. It does not oscillate at any other frequency. Okay. So, no harmonics. It gives you a nice clean sine wave. So, for example, if you want to synthesize the sound of a flute, okay, sound of a flute is a pure sine wave if you play it nicely. Most other instruments can have harmonics, usually they have a lot of harmonic content, other instruments. Flute can be made to sound like a pure sine wave, right, and if you want to synthesize the sound of a flute, this is the way to do it. Okay, this is one of the few circuits that can actually synthesize the sound of a flute. Otherwise, you will have to do a lot of other complicated, you will have to have a DSP, A to D converter, D to A converter, right. You will have to generate the codes in a digital form and then do digital to analog conversion, and that also will create harmonics and so on and so forth. Okay. Then filtering and so on. So, sine wave oscillator, this is one of the few sine wave oscillators. All right. Most of our other oscillators are non sine wave, they start generating square waves, triangular waves, all kinds of other things, right. This is one that gives you a sine wave. This is called the double integrator oscillator. The reason why it is called double integrator is because the first stage is an integrator, the second stage is another integrator, third is just -1, right. You need the -1 to create the negative DC feedback. All right. The negative DC feedback is going to make sure that this op amp is under control, its minus terminal. If it increases slightly, there is going to be overall feedback and it is going to decrease. Second one is also going to be under control with the help of DC negative feedback. Okay. So, let us stop here. In the next class, we are going to switch a little gear and we are going to change gears a little bit, and we are going to start discussing other things. Okay. Thank you.